This screencast is looking at linear regression. So what is regression analysis? It's a statistical process that we use to estimate relationships among variables. In most cases, regression analysis is used to help understand how a general value of the dependent variable changes when a single independent variable is varied and all other independent variables are remaining fixed. To establish a meaningful relationship or model of the data, it's important that in linear regression that only one independent is varied at a time. This relationship or model is a function of the independent variables and is called the regression function. We use this to estimate our conditional expectations of the dependent variable given the independent variable. In other words, we're looking at describing a regression line. For the purpose of this module, you can imagine regression analysis is a technique where we're estimating a value of dependent variables which are actually continuous. It's one of the most studied types of regression analysis, and it's usually used for predicting values of y given values of x. However, you can also look at the strength of a relationship, and on occasions you might look at several values of x, or look at independent variables which should be left out of the model. The general form of a linear model is shown below. In the second line, the response, y, here's y in our top line, it's just a function of a coefficient multiplied by a variable x. And in the second line here, we're saying the expectation of y given x is this, which is actually the formula for a regression model where you've got x is multiplied by betas and you've got some error. And the variation of the variance of y given x is sigma squared. We have to have assumptions for linear regression, and this is generally concerning the characteristics of the data, and so we typically want to make sure that our results will be useful and that the data analysis will be valid. So if we consider that we have predictors and we have a response variable and we've observed them on a number of cases, we want to consider that we've got errors that are associated with each measurement are independent, and the data points are actually independent, so that we've got no correlations in there and we've got sort of random data points. We want to consider that we've got constant variance, and this implies that our conditional variance of the response given the predictors is fairly constant. Lastly, we think about the variability of our residuals, which is the values of the individual values taken away from the repeated values. So the residuals, which we'll talk about later, must fit a normal distribution, and so the expected values of an error is 0, but there's a variance associated with that. So in general we have measurement error. Let's generally look at a little example here. We're considering we've got some data from student grades, and we want to just check whether there's a linear relationship between a student's GPA at school and their performance in a national exam. So it's a simple example just to give you the principles of regression. There are many ways to bring data into R. One of the easiest ways, if you've got it, is within your project folder. If you don't, remember that you can very easily bring it in using the import data set, and you just usually bring it in as a CSV file, and then you use the from text file option. And in this case we might need to adjust. So in this case I'm looking at, this is importing the data set, so it's like a wizard that comes up. It's showing me I've got student, GPA and score, and I need to have a heading because I've got the variable names at the top, so the heading needs to be ticked. When I look at the data frame that's going to come in, that looks sensible, so I can use import, and then when I follow through this data set, which is called grades, you can see the name here with a capital G, will come into my R, and there I will have my data. So one of the first things we might want to do with our regression data is to be familiar with how we might just work with regression. The first thing I'd like to say is let's plot the data set of interest. Let's say we have this data set with GPA and score, where score was the dependent or the response variable. We'll plot it, and we just use this very simple code. Plot, open brackets here, score tilde GPA, and then we have our data. Data is grades, and when I read it in, I did use a small letter for the G, so this must be case sensitive and must match what you've called your data when you read it in. That's what I'm calling it. So here we can plot, and the output from that command gives you your GPA here on the X and the score on the Y, and you can see there's a bit of a relationship, but we don't know yet. It does appear to be linear, and so if it is, we might want to fit a linear model using the following code. And this again is very easy. First of all, you can see we're using our data equals grades. We're fitting a linear model, well, this is LM, open brackets, score tilde GPA, so that's explaining our linear model. And this is the less than sign dash, which means we're going to assign this model, this is the model, we're going to assign it to fit1, and this is the name that we've given it this, we're calling it our linear model fit1. We can also plot the scatter plot for a line, and what I've done here is I've said put an AB line on my linear model. So I'm using that linear model, and I've put a brackets around it, and I've asked to do a regression line. This adds the regression line to the scatter plot, and that's the result. Now our model has been fitted, we haven't yet looked at the results, so we want to obtain a summary of the model to observe the output which describes the relationship. So we can use this simple command, summary fit1. When we use this command, we're requesting the linear regression output for our linear model object, which we've called fit1, and the following data is produced. So this is the output from that summary fit1. It tells you what the linear model is, so here we are at the top. Then it gives us some idea of our residuals, and it's saying that our residuals have a minimum and a max, just gives you that. It also gives you coefficients, gives you an intercept, and in fact this is the slope. It gives you an estimate of those, and so this is the estimate here, and the standard error of that estimate, and a test, a t-test, to see whether they're significant or not. So the intercept is not significantly different than 0, but the slope is, and we've got a significant slope here. Okay, there's a few other things here which we'll discuss later. So we have to understand the output. We've got the call, we've got the summary of the residuals, and we look under the heading coefficients. It gives the estimate of the intercept and the slope with their respective standard errors, and the residual standard error is an estimate of the parameter. The R-squared coefficient is also known as the coefficient of determination, defines the proportion of variation in values of the dependent variable that can be attributed to its linear relationship with the independent variable. Let's pop back to see what that was. Here's a residual standard error here. We've got a multiple R-squared here. So the R-squared is 0.57, and with adjusted R-squared is 0.53. They're not very different. And you've got an F statistic here and a p-value. This p-value is for the regression, and it shows that it's significant because it's less than 0.05. So here, you can look at this in your own time. It gives you about the adjusted R-squared. This is more when you use more complex models. We're not going to look at that today. The t-value is shown for both the slope and intercept, and the p-value gives whether the t-value, the probability of achieving a value of t, and so the null hypothesis that the coefficients are 0. And then we've got the p-value, which is, we look at it and say it's significant if it's less than 0.05. So we can also get analysis of variance for regression, and so we've had some of the data, but we can actually use this ANOVA of our linear model, and we're just going to say ANOVA fit1 because that's what we've called our model. And here you get, this is actually set out like an ANOVA table. Here's the probability and the F value that we had on the previous output, 2 stars, and here's our residual mean square that we can use if we need to in any of our calculations. But we can ask R. We can actually get it to give our fitted values, so we can say fitted of fit1, and that gives us our fitted values for the 12 students. We can get the residuals for fit 1, and we get the residuals, and so very easily you could plot those together. Notice here we're saying fit 1, which is our data set or the object, and we're asking it $ says fitted values. Here we're saying we want our object fit 1, $, we want the residuals, and we plot them against each other. The other thing we can do by just using, first of all, we can put in this small matrix command at the top, and if we just say plot fit 1, that's going to give us this very nice residual plot, which are 4 different plots. This is residuals versus fitted, which is exactly what we've just done. And here we've got a normal QQ plot, theoretical quantiles versus standardized residuals, and if these lie on a straight line, that's very positive to show your data from a normal distribution, and these other two are not as useful, but you can get that's a residual plot that's quite nice to have a look at. You can also get confidence intervals, so, and I'm also going to show you here there's a thing called coefficients of fit. So if you just wanted the intercept and the slope, we can just ask for coefficients of fit, but we can just as nicely ask for confidence intervals of fit, and we're saying we want 95% here because we're saying level equals 0.95, and here we get, you can see here, this is our 95% confidence intervals for the interval here, and for the intercept, sorry, and for the slope here.